Hello, we're going to take a look at part of a class assignment for Virginia Tech's Software Defined Radio course and general ideas for implementing the enhancements that were assigned to the students in the class. Okay, so as mentioned in a previous video, these blocks at the top of the screen are primarily variable blocks. Some of them are adjustable by controls such as sliders. The simulation uses two signals, and so we have a signal source here, another signal source here. We have two elements in our antenna array originally, so this will be a phased array but with just two elements, and for convenience we selected one of those elements as a reference and the relative phase of the two signals, regardless of their angle of arrival, as a reference, and we'll just call that 0. However, the relative phase shift between the signals from the two different transmitters will change at the second element based on the geometry, including the spacing between the two array elements, or the two antennas that make up the array, and the angles of arrival of the two signals, which originate from two different transmitters that we'll be able to see in a polar plot in the graphical user interface. These blocks above and below the second signal source apply a phase shift due to the transmitter angles of arrival. They apply that phase shift both to the signal from transmitter 1 generated by this signal source. We generate this phase shift based on its angle of arrival, and we multiply the complex signal by this phase shift, which will shift it by the specified phase shift. And we do the same for the second signal. So what we do is we have at the second element, this is not the reference element, the two signals incoming from the two different transmitters. They each have a phase shift due to their geometry, including the angle of arrival of the signal and the geometry of the array, or the spacing between the array elements. And we've applied that phase shift to represent the geometric effects. We then add those two signals together just as they're added at the second element where they're both received. And after they're received at the second element, we add yet another phase shift, which is a phase shift between the two elements that is specified by the user using a slider. And so that phase shift comes from these blocks here. The signals from the two transmitters are each displayed in a spectrum plot over here after passing through the channels in which noise is added. A third input to the frequency plot is used to display the signal at the array output. The array output includes the sum of the signals received at element 1 and the same signals as received at element 2 with the phase shift applied. Again, the phase shift is selected by the user. We're not doing adaptive beamforming. It's all manual at this point. So those two signals from the two elements, in the case of the second element with phase shift, are added together and sent to the frequency sink. The first task is to add one or more elements or antennas to the simulated antenna array. This will require modifications to the flow graph, mainly in three places. First, we have a group of blocks that is used to generate the frequency plot. Currently, we're only applying an inter-element phase shift to one of the elements, because the other element is used as a reference where the relative phase shift between the signals from the two transmitters in the simulation is used as a reference. So the phase shift at the second element is relative to the phase shift between the two signals at the first element. And so we add a phase shift using a slider. We can select what that phase shift is, and we're adding that phase shift to the received signal from the second element. And that second element receives signals from transmitter 1 and transmitter 2, and the relative phase shift of those signals as received at element 2 depends on the geometry, in other words, the angles of arrival of the two signals. As you add elements to the array, you'll need to do something similar for each new element to what is done for element 2 in the original simulation. That is, you will need to apply a phase shift at each new element that represents the effects of the geometry. So that would be this series of blocks here and this series of blocks here above and below the second signal source. Additionally, you'll have to apply a phase shift to the combined signal at the new element, and at each new element you'll have to do this. That phase shift will be related to the selectable phase shift in the current simulation. However, it will also depend on the spacing between the elements. I recommend that you keep the spacing between each pair of adjacent elements equal, and that you keep all elements in the array collinear. In other words, they'll all appear along the vertical axis on the right side of the GUI. And I'll leave it to you to decide how best to implement these changes in this upper part of the flow graph that is used to draw the frequency plot. There are two more places where you'll need to make similar changes. Two additional collections of blocks in the flow graph are used to calculate the array pattern using the ideal inter-element phase shift and the array pattern using a quantized version of the inter-element phase shift that will contain some error due to the lower precision used in the quantized version. In this case, you'll see a set of blocks near the top of this larger collection of blocks, and one of these is used for each of those patterns, for the ideal pattern and for the pattern with the quantized phase shift. So one is near the top of this part of the flow graph and one is near the bottom of this part of the flow graph. Each of those is used to generate an array pattern that includes the combined effect of the element positions and the inter-element phase shift, but not effect of the geometry of the transmitter's angle of arrival of the signal. Therefore, each of these collections of blocks that's used to generate an array pattern includes a signal that represents the reference element, or a component that represents the reference element, and another one that represents the second element with the inter-element phase shift applied. There's a lot going on in this part of the flow graph, but the basic idea is that we're tracing out array patterns and concentric circles or grid lines on a polar plot that's generated using the QT constellation sync. Additionally, that constellation sync displays the element locations, which can be adjusted by using a slider to select the inter-element spacing, or the spacing between adjacent antennas within the array. So we have the antenna positions that appear as green dots in this case, and we have some grid lines actually generated using these blocks. Here are concentric circles just used for reference in the polar plots. We also have the transmitter positions that are also displayed towards the outside of the polar plot, so we can see the angle of arrival of each signal based on the position of the corresponding transmitter in the polar plot. So what we're really concerned with is the two collections of blocks that calculate the array patterns and generate those array patterns, and the collections of blocks that specify the array element locations. You should be able to figure out what changes to make once you understand one additional thing related to the polar plot. In order to draw things like concentric circles and array patterns on the polar plot, we need to sweep over a range of angles. And to do that, in this case, I've used a cosine. By default, it has an amplitude of 1. I've multiplied it by pi so that the value of that cosine function that is output from the signal source varies between negative pi and positive pi. And we can convert this to degrees if we want to, or we can leave it in radians and use that as the angle for calculating the array pattern. And as that cosine signal goes through that range of values that correspond to a range of angles. We use that as the phase input for a complex number, and we take the magnitude that we calculate that also corresponds to the phase from the signal generator. So we use that cosine signal as a phase reference. We're using it up here, we're using it down here, we're using it for all the grid lines or concentric circles. We don't have to use it to plot the array elements. They're just dots that are along the vertical axis in the center of the plot. And so keep that in mind. And that's the importance of this signal source. It's just to generate that full range of phase angles over time. And in a newer version, I've actually replaced the cosine signal with a sawtooth wave and set the constant multiplier so that that sawtooth wave in a linear manner varies over the full range of angles to serve as a reference and to do that in a little more linear manner. Also, you may consider changing the sample rate for the signal source block here. If it's too high, it would result in unnecessary calculations, so you might want to change it from what you see in the example. And basically in each of these array pattern calculations, you see a constant that represents the contribution of the reference element, and that's added to the output from all these other blocks that represents the contribution of the second element with phase shift that depends on the spatial angle generated by the signal source. For every angle, we calculate the magnitude of the array pattern and then use that as a magnitude input for our magnitude to complex block, and the phase input for that is the output of the signal generator. So for every angle, as we sweep around the 2 pi radians, we're calculating array factor at that angle, and we're inputting that as a magnitude. We're inputting the angle as phase, converting the two to an ordered pair, which are also the real and imaginary components in a complex type number, and we're sending that number to the constellation plot where that point will be plotted, and then the next point will be plotted for the next angle, and so forth until we've traced out an array pattern. The second enhancement that I've asked you to make to the flow graph and the simulation is to simulate beam squinting. The idea here is that the array pattern will change and the angle of beams generated by the array will change depending on the frequency of the signals that the array is used to receive. And the basic way to implement that is to assume, as is done in the original simulation, assume that the element pattern that you see is generated based on the assumption that the element spacing in wavelengths is as you've selected using the slider for some nominal or reference frequency, and that frequency is implicit right now, so we'll just consider that as a factor of 1 and consider any other frequency where those transmitted signals might actually be as proportion of the reference frequency. In other words, the actual signals could be transmitted at a lower frequency, let's say half of the reference frequency, or they could be transmitted at a higher frequency that will be perhaps twice the reference frequency or some other number, but I would just give those as examples, and that number, that ratio between the actual frequency and the reference frequency can vary along a continuum. So a slider would be a good control to use to allow you to vary that parameter. And the element spacing is specified using a slider in wavelengths, but those are wavelengths at the reference frequency. And the ideal array pattern is calculated assuming that the signals are at the reference frequency, and it uses a wavelength that corresponds to the reference frequency. You'll also want to plot a non-ideal array pattern, and that will be the pattern of the array at some frequency other than the reference frequency that you select using that slider. So it'll be a higher frequency or a lower frequency, and in that case, you should use the wavelength that corresponds to the selected non-reference frequency in your calculation of the array pattern at that frequency. So you have an ideal pattern, that's the pattern based on your phase shift selected at the reference frequency. You have a non-ideal pattern that will be the pattern at the other frequency that you've selected that's not the reference frequency, and those patterns in general will differ from one another. And you should be able to see the beam squinting effect that we talked about in the class. When doing this, and when making all these updates, you want to keep in mind the QT GUI constellation plot. This appears to affect at least one version of GNU Radio based on reports from a student in the class. And that limitation is that although the number of inputs to the block can be increased arbitrarily using the block properties, the QT GUI constellation plot only actually appears to process the first 10 inputs. And if you notice in this flow graph that we're using as an example and a starting point, 10 of the inputs are used, leaving no place to add positions of additional elements or potentially additional array factor plots. So as you see, we have 4 of these grid lines, and that's taking up 4 inputs to the QT GUI constellation plot. It would be nice to have all 4, but if we need to add something else to the plot, these are the most expendable inputs. So I would just use 2 of the grid lines rather than 4. It's easy to disable or remove them. You can also go into the constellation block and make changes as needed. The third enhancement that I've asked you to make is to add an element pattern. That is, assume that each antenna used in the array is not a simple omnidirectional antenna, and assume instead that each of those antennas that make up the array, that is the elements of the array, has its own pattern, and further assume that all of the element patterns within the array will face in the same direction at any time. By using a directional element pattern, you will be able to suppress parts of the array factor in the resulting array pattern. In other words, the array factor or the array pattern that you would get using omnidirectional elements may have beams or nulls in places where you don't want them, especially beams. Using directional elements, you can mitigate that to some extent. And if you recall our discussion of grading lobes earlier in the class, showing the effect of directional elements on grading lobes would be a great way to demonstrate that your directional elements are working properly once you've integrated them into the flow graph. Now you might ask, where do you add the directional elements? And there are a couple places where you need to do that. What I did was make the directional element patterns part of hierarchical blocks that apply a directional pattern to a signal, but that is selectable using a variable in the QT GUI chooser widget or block from GNU Radio, so that you can either apply the element pattern or just leave the original assumption of omnidirectional elements in place. Further, one of the parameters of the directional element block is the direction that the beam maximum of the directional element is facing is selectable by a slider. The fourth enhancement is to add dithering of phase shift values, which should help when we're using quantized phase shifts.